Good. See? That's what? I thought that. Yeah, good stuff. G'day, I'm Marcel Jackson, a mathematician at Trobe University. I want to talk now about not algebra per se, but something very closely related to algebra, which is the theory of ordered sets. So you'd be familiar with ordering things. That's not very profound. Let's look at an instance though. When you go to vote, let's say there were 4 candidates, you're asked to put some numbers in these boxes, 1, 2, 3, 4, according to your preference. And very often you will see a situation where you may be very sure as to who you want to give 1, some candidate you really like, and very commonly there's a candidate that you very much dislike. And then you get some intermediate candidates, and really you probably have trouble deciding which of these gets a 2 or a 3. And you're forced to give it some ordering because the kind of orders that we ask people to use on a ballot paper are quite strict. They're what I would call a linear order. But in the theory of ordered sets we get much more complicated orders where you're allowed to have 2 objects that are not actually related at all. So we might want a situation where we liked 1, we quite liked 2 and 3, but we couldn't really place them, and we definitely disliked 4. So 2, 3 and 1 were all above 4, and 1 was the favourite. So a very good instance where these kinds of things might arise might be in management structures, where maybe this is the boss of an organisation and these are 2 different arms and they might communicate with someone further down. In fact, a particularly good instance of this is actually terrorist networks, and ordered sets are actually used in studying the structure of such things. Because there you have a situation where the leader of this organisation communicates with subordinates who communicate further down the line, and in order to make things a little bit more robust, the people down here don't have any way of communicating with the person at the top. This is sort of true in a business, actually. The general workers don't directly communicate with the executive board. And so you get interesting problems about how you might try and capture some terrorists and see whether or not the leader can still communicate with the foot soldiers. If you want to play with this kind of thing at home, there's a very interesting instance that's also very important, which is in the study of stacking boxes. So this might arise if you own a factory, or if you're trying to organise the stacking of containers at a dockyard, for instance. And you can play this with books. So this is actually a hidden piece of complexity in your own bookshelf. If you take some books, there's a natural ordering on them. For example, here, this book on Frege is quite small, and I can put it on top of this book on dynamic logic without any overhangs. I'm going to ask here that the binding matches up nicely. So here's where we start to get some interesting things. This book, Structural Topology, very wide. And you can see that I can't really put these next to each other without creating some kind of overlap. If I put dynamic logic on top, then I get an overhang at the top with structural topology. And if I put structural topology on the top, I get an overhang as well. So if I rub out this here, you can see I'll actually get a picture from this. Structural topology, dynamic logic, they were sort of incomparable. It wasn't true that this was bigger than dynamic logic, and nor was it true that dynamic logic was bigger than structural topology. They were sort of different. On the other hand, Frege could be placed on top of either of them. And maybe then I get out an atlas, which is really big. I can put the atlas underneath both this one, and therefore also that. This was actually the same kind of order I wanted to do for my candidates. So now we have an interesting problem though. If we want to stack our books, and you can do this at home, get out some books, and we want to create the smallest number of stacks that fail to have any of these overlaps. This is actually a very challenging problem, and you can see it's exactly the problem that you would be faced with if you were receiving a lot of containers and you needed to stack them in the most efficient way possible. So this is a real problem, and actually you can play with it yourself at home using books.